On the left-hand side, we've got a reservoir that's kind of that fairly low stage at the moment. And these Tainer gates are set up. We're looking at them from behind. And the reason that they were developed is because in a number of places you would get debris that would gather at the dam spillway, right? And that would alter the hydraulics of the spillway. And so the way that these work is they're rounded. You can see the picture on the right. There's kind of this cross section of the way they look, and we'll work a problem like this in later today in class. But you try to lift this up, and so you're basically allowing water to move out the bottom rather than go over the top. And when you do that, you can trap all of the debris up here, and it doesn't have to affect your hydraulics. Okay, but there's a really important engineering question here, which is what are the forces that are acting on this gate that you need to oppose in some way, right? Some FR, let's say, to keep these stable, to keep them in place, and to keep them usable. All right. Before we get into curved surfaces, I put a few poll questions together to just kind of jog our memory on a couple of things. So go ahead and pull out your iClicker or get your Reef app going. It looks like I need to go back there. Let's see here. Yeah. Okay, where did my Reef? There it is. Okay. I'll get class started here. And okay, we'll bring this guy front and center. Hope he stays there. Okay, there he is. All right. So let's move forward here. Okay, so there's a series of these questions, but here's the first one. A two-dimensional gate is submerged in water. So this is the plane gate that we've talked about for a couple of classes now. And the question is, the figure that best represents the pressure distribution of the water on the left-hand side, the water side of the gate, is which? Is it A, B, C, D, or E? So let me, where am I? There we go. I'll get the poll going now. So we're counting up to a minute. Which one of these, A, B, C, D, or E, best represents the pressure acting on the gate? And think carefully about the way that we've represented pressures throughout. All right, we're up to 76. Let's see, how many folks do we have today? 96, I think. So should get a couple more. 93 might be our limit. Oh, no, we got 95. Oh, maybe it was 98. That number was really small. So, okay, I think that's probably going to be it. So I'll just wait till we get up to a minute. The anticipation. All right. How did you all vote? All right, 3 of you said A, 53 of you said B, 11 of you said C, 3 said D, and 26 said E. So B and E are kind of the two front runners. All right, so let's talk about this. Remember that, let me do this with my pen here. Remember that we have said that, I'm just going to take a point over here so it's not associated with the gate itself. Remember that from this point of reference, we have an increase in pressure as we go down, and that this slope is related to whatever the specific weight of the fluid is. So in this case, we're told it's water, so we know it's 9,810 newtons per cubic meter. However, we've also said that pressure works in the same, or at the same elevation. Pressure is acting in all directions with an identical magnitude. Okay, so that means that when we get to this sloping gate, we are going to have some kind of right angle. So it's going to be D or B or A, because those are the ones that tell us that we have a pressure that's at a right angle to the gate. Now what that means is that if we were above the gate, we would have, I guess it would be, sorry, I should have made that a little bit bigger. Anyway, it would be increasing, but we would have pressure that is acting as it increases on that wall, perpendicular to the wall. When we transition to the gate, we are going to change that direction, and it's going to act perpendicular to the gate. Okay, so A, B, or D should be the one that we have. Now, some of you may have thought E because we often think about that increase as we move down, but the increase in pressure, but that's just a representation of how pressure changes. The actual interface of pressure with a surface is always at a right angle. So we have to have D, B, or A, okay? All right, now let's take this a step further. Could it be A? If we look at A, one of the what it's showing here is that we have some location that starts from about zero pressure and increases. So this one doesn't work for us only because we note that we're starting with some depth already over us, right? The top of the gate is submerged by who knows how many feet or meters of water, but regardless, there's already some pressure built up. So we should not start at zero at the gate. It should have some additional pressure on top of that. In the case of D, it can't be D because if all of these are the exact same value, right? They're all the same magnitude, those pressures. And we know that as we go down the gate, we must have increasing pressure. So ultimately, that tells us why it has to be B, okay? So these are the types of questions that you might see on the first part of the exam, by the way. These types of multiple choice, conceptual questions that, well, if we were doing this on paper, it might be a little bit different, and you might get the top part of this without the answers and say, draw the pressure distribution, right? And we can't do that very easily. So just to give you a sense of what you'll see, and you'll get a sense after when I post some materials as well. So just as an FYI, a little bit of an aside there. Okay, so does that make sense to everybody? All right, so let me go on to another one here. All right. So a tank of water of depth H that is open to the atmosphere is shown, well, at the side, not below. There's a rectangular plate located on the left-hand side of the bottom of the tank, as shown. The location of the resultant pressure force, or the center of pressure, on the plate, X sub C, is given by which of these five equations, where all of them are related to H or L, okay? H is the height of water that happens to be the current stage inside of this tank or whatever it is. And L, in this case, is the length of this plate that we care about. The plate is horizontal, all right? So go ahead and give you guys a minute to think about that one. A, B, C, D, or E? Is it mostly, is the location of the center of pressure a function of L or a function of H is essentially what this comes down to. And then which? Yeah, don't read too much into the location of F and X sub C. We're just trying to indicate some generic location. So don't try to think about this. Is that like 2/3 of the way across? Is that 1/3? That wasn't the goal here. Okay, we're up to 90 responses. 95, do we get to, all right, 96. 97, I like it. Anybody else? Okay. Let's take a look. All right, so the answers, so nobody liked E. That's good. We don't like E. D was the most voted. C, B, and A all had 8 to 17 votes. All right, so let's take a look at what's valid here. When it comes to pressure, remember that at the same elevation, the pressure is identical. So if we were here, all pressures at that elevation are the exact same because we said that dp dx or dp dy, so the pressure change in either of the horizontal directions, is zero. And pressure only changes in a hydrostatic situation here with depth. So one thing to note then to start with is that the plate, being horizontal, flat on the bottom, has even pressure distribution across it. Okay, the same pressure is acting at all locations across that plate because it's got a horizontal orientation. Okay, so that's what the pressure does. If we were going to calculate the force, the resultant force of pressure, we would have to account for this depth of water, H, and sort of figure out, okay, well, how much of this water is piled up above me? In this case, when we're looking at the location of X sub C here, we're looking for the line of action through the center of this. It does turn out to be D, L over 2. And the reason is, again, because all of this is evenly distributed, this pressure, essentially it's just going to be acting through the center of this plate. So for the dimension that we've identified here, it would be L over 2 halfway across the dimension that we're seeing here. All right. Okay, I've got one more for us. Okay, a tank of water open to the atmosphere with a depth H is shown below. The left side of the tank is at an angle. Okay, so we've seen this before. The location Y sub H of the horizontal force FH on the rectangular plate is given by which of these equations? In other words, how high up, where YH note is coming from, it's a height above the bottom of this. Okay, so we've used Y in a slightly different way to kind of measure down from above. So just note a YH here is coming up from the base. All right, so where does that act? Let me give you a minute to think about it. Go ahead and start voting. Is it a third of the way up, L over 3 the way up, H over 2, L over 2, L minus H over 3? All right, 20 seconds left. Not sure if this one makes you think more or we've lost a few people. Oh, we're getting over 90. Okay. 4. Can we get back to 97? 95, good. And maybe we had one drop off. Okay, let's go ahead and stop and take a look at the distribution of votes here. All right, so, sorry, let me move that a little bit. Okay, so the highest voting was for A. We had 44 votes. B had 16 votes. C had 26 votes. D had 4, and E had 6. So we can go ahead and eliminate D and E. And part of the reason with D, of course, is that the pressure will change along this face, but only as a function of depth. Okay, and the dimension L in this case matters in the sense that it's related to some H, but the line of action for FH is still about a pressure prism that is acting along L here. Okay, so L over 2 doesn't work out. L minus H over 2, I don't quite know where that would come from. Even if L was changed to some different angle, there's to my knowledge, there's not a good reason to try to take this difference and sort of look at that and then divide it by 3. Let's go back up. All right, C was a popular one. So H over 2. H over 2 would be a location where we would take the average pressure to figure out FH, the horizontal force. Okay, that's good. But let's take it a step further. Remember that when we were talking about pressure prisms and when we used the moment of inertia to figure out the y sub r, where the resultant force was acting, in each one of those cases, we ended up going down 2/3 of the way through H, okay? So as it turns out, H over 2 is a good location for picking the average pressure. It's not the right location for picking the line of action. In this case, we can actually identify A as the right value because you can imagine that whether the wall is vertical or tipped on its side, as long as there's H amount of water there, H height of water, or whatever the fluid is, in this case it's water, there's still a pressure prism to be drawn there. And that pressure prism then is going to act 1/3 of the way up through H, all right? Regardless of how we have that tilted, how we have the wall tilted. So Y sub H should be 1/3 of the way up through H, all right? Okay, terrific. All right, let's move ahead then and talk a little bit about what happens on curved surfaces. I hope that one of the things you've started to figure out is that there's a fair bit of geometry involved here. And so the geometry of our circular parts or rounded parts of our interfaces will be no different. We just need to start thinking about things in a slightly different way. However, as we were looking at on these little challenges you just had with voting, we are still going to have a linear increase in pressure, right? That doesn't change regardless of how curved the surface is. So that will not change, but what will change is how we think about the way that forces are interacting with the fluid. So remember over on this this right-hand side where we are vertical, we could think about, you know, some FR acting to oppose the FR on this side. Sorry, maybe that wasn't some resultant force, you know, and some, I don't know, pushback force or structural force. Let's call it that. Maybe F sub S. That's a terrible S. Structural force that is holding back FR. But when we transition to start talking about what happens down below, where we have this interface, this curved interaction, automatically we transition from a horizontal force to a completely vertical, which means that we're going to have a force that is going to have two components to it, right? It's some X and some Y component so that it all works out here. I'm going to move this guy out of my way. Yeah, I think I did. Okay, so let's identify a couple of things. Number one, let's take this little wedge of pink water as it's identified here, and you can see that we've kind of created a domain from C to B to A. All right, so C curves up to B, and then we have these straight line interactions between A and B and A and C. All right. What does a force balance look like here? All right, first of all, F1, as you might expect, is going to be, it's vertical. And it is due to basically the overlying fluid pressure. Okay, so F1 is just adding up all of whatever pressure we have that gets us to this location. You know, we have to have that pressure acting downwards on this location, and then we also have some F2 acting from the side. Okay, so F2 we're going to represent here as being horizontal And that one is going to be due to the fluid next to us. Oops, there's no L there. Fluid. I'm just going to say adjacent. Okay, so, and the reason that I write that is we will again see like some sort of offset here, right? And then we'll have this increase in pressure or whatever. Okay, so there's some F2 that is the resultant force of that hydrostatic pressure distribution on the left-hand side. And then, of course, we also have, within this domain, we have the weight of the water that is in this domain. So if we were working a problem, we would know that this wall is, I don't know, 10 feet across or something, right? So we could look at an area here, some area, and multiply. Wow, that's terrible. Some area, and multiply that cross-sectional area by some depth, let's say, or width into the page to get that full volume, right? And that volume we're just going to multiply by gamma to get the weight force, all right? So so what I want to set up then is all of this looks fairly simple. It's all working in the X and Y directions, right? So this FH, this counterforce that is going to have to keep this curved section in place and oppose the incoming forces, FH is equal to F2. Okay? And we would say, similarly, that FV, the vertical resultant force that's holding back this water and keeping the curve in place, is equal to, now we've got a sum. We have the weight of the water plus that water, that the pressure that's coming down from above. So W plus F1 in this case. All right. Now, the true resultant force that acts here, we're not going to give up the geometry completely, but what we're going to do is embrace the Pythagorean theorem here and say that, well, the resultant force that's going to go through O, and we're basically just going to take the sum of the squares of FH and FY, okay? The square root of the sum of the squares, sorry. So you can imagine then that we're not taking the square root of F1 squared plus W squared plus F2 squared. We are working through the sums to work in an X, figure out the X component of FR and the Y component of FR to keep this in place. Then we take the square root of the sum of the squares of each of those components. Okay, so we do the addition first of F1 and weight, for example, to figure out what FV is going to be, and then put that into the Pythagorean theorem. So this is maybe what we would call some FR being equal to these the square root of the sum of the squares of these two components. All right. One more point that I just want to emphasize, and I'm going to write it on here, is that I just want you to note the focus on, in this case, we had the reaction forces F, H, and FV, and we didn't go trying to take the square root of the sum of these, of W, F1, and F2, okay? So these are the ones that give us this resultant force here, all right?
Professor, is O just a location, or does it represent something else?
Thank you. Yeah, O is a location through which the resultant force acts, and we could spend a lot of time looking at the moments of the vertical and the horizontal from, let's say, the center or something like that, some reference point. In this case, O is a point that the resultant force acts through, and that it's also going to go back to, in this case, the center of this radius, right? If we have a constant radius, it'll go. Well, I'll show you that in the next slide, because we're gonna go through a problem that has a conduit that's round, and so it'll go through the center of the conduit. But in this case, it would go through the center of the curvature of this section, right? We don't really have a circular cross section. We have kind of 1/4 of a circle, and so yeah, O is just a location through which this resultant force is going to act. Thank you for asking that. Alrighty, let's put this to use somehow. All right, what do we need? Here is well, it couldn't. I guess the picture on the left, I sort of didn't take this for granted, or didn't think about it very clearly. I don't think that man is so tall that he has to squat to get into a 6-foot diameter drainage conduit. But anyway, let's say that we have a 6-foot drainage, 6-foot diameter drainage conduit. Shown here, running half full of water. All right. And it's let's assume this water is at rest. I forgot, when I say running, I forgot we have to remain in static mode. So we'll do that. The question is, what can we determine the magnitude and line of action of the resultant force that the water exerts on a 1-foot length of the curved section BC of the conduit wall? Okay. So BC, here you can see we're going to again have this sort of little fourth pi wedge here that's about 1/4 of the total circle area, cross-sectional area. And in this case, when we say 1-foot length, that means into the page, right? Or out of the page. So we can look at a 2-dimensional area here. To make it a 3-dimensional area, we just multiply by 1 foot because of the way the problem was written. Let's say this was a conduit that was going under, a 2-lane road, right? This may be something more like 30 feet long, and maybe we want to know the force to keep all 30 feet in place. Maybe this would not be 1 foot, it would be 30 feet to just figure out that total force. So in this case, we're just going to look at it on a per foot basis, per foot length. What is the force that we need to keep this water in place, all right? From just one side of this. All right. So we go back to our force diagram here, which is similar to what we saw before. We've got the weight of our volume of water. Remember, it's going to go 1 foot into the screen here. So we've got weight that we have to worry about. We have some hydrostatic pressure, right, that is over here that is acting to give us this F1, okay? So one apology to you real quick. And both of these are taken from your book. So the F1 before, I believe, was vertical, and F2 is from the side, if I'm not mistaken. Yeah, and now we've put F1 to the side rather than vertical. So one thing that's different about this problem is that we don't have any fluid above AB. So we don't have a pressure pushing down from above. So what this means then is that the horizontal force that we need to use to keep this pipe in place is going to be equal to the vertical force. Am I right? Yeah, FH is equal to F1, and the vertical force, FV, will be equal to the weight of the water per foot length of this conduit, okay? So F1, we can also write, and let me just put down our master equation here, which is to say that the resultant force magnitude will be equal to the square root of FH squared plus FV squared, okay? All right, so let's figure out what FH and FV equal, and we're going to do that by figuring out the weight of the water in this 1 foot length and to give us FV, same magnitude, and F1 will be equal to FH, and F1 is simply equal to gamma, in this case of water, times some depth to the centroid, right? So in this case, that's going to be whatever height this is from, I'm just going to note HC, the centroid location or depth, is equal to H from A to C, whatever that length is, divided by 2, right? Where this is A to C, that chord, so to speak, in our shape. All right, and then we're going to multiply by the area of that interface on the left-hand side. So this area that sort of goes from A to C and goes 1 foot into the page. Now, we were given that the radius of this, the diameter was 6 feet, right, of the conduit. So the radius is 3 feet. So I'm going to write this then as, that was supposed to be curved. All right, 3 feet by 1 foot. Okay, so that is a rectangle. What is a rectangle doing in our conduit? Well, it's just acting from the side onto a 1 foot width of water and a 3 foot height of water, that rectangular interface on the left-hand side. All right, so let me make sure those look like they're distinct from each other. So this would be equal to, we're working in feet, so this would be 62.4 pounds per foot cubed for our specific weight of water. H sub C now is going to be this height. So we said that this length is 3 feet divided by 2. So this ends up being 1.5 feet for H sub C. And then we multiply by, basically, I'm just going to simplify this as 3 feet, 3 square feet, 3 feet squared. Okay, so having done that math of 1 times 3. Now, when we work this out, we will get 281 pounds of force is F1. Or maybe I'll just take it a step further, call that FH, right? We said F1 is equal to FH. Okay? All right, now what about the vertical force? So in this case, the vertical force we said is equal to the weight. And to figure out the weight, we need to get the total volume of water we have there and multiply it by gamma, right? So gamma water, gamma water times the volume of water we're talking about here. And so the volume of water we're talking about, so I'll just go ahead and write this out, I guess. We know that we're going to have 62.4, I may have to copy that over, but anyway, 62.4 pounds per foot cubed. It multiplied by pi over 4 times the radius squared. Okay, some of you are automatically thinking, oh, that doesn't sound right at all. I don't like that because this isn't a diameter. True, but we're basically pi times r squared. Oh, not cubed. That should be squared. Pi r squared is the area of the entire circle. We only need 1/4 of that. So I just went ahead and combined the pi and the 1/4. All right, so pi over 4, because we only want 1/4 of the total area, times r squared. That'll give us 1/4 of the cross-sectional area. And then remember, our depth is 1 foot, the distance along the conduit. Okay, when we work this out, we end up with 441 pounds. Okay, now the kind of neat thing about this then is to think that this pressure force that's acting on the left side of our wedge is a little more than half of the weight of the water as it is, right? So there's a lot of vertical force acting here. All right, so now we can solve for FR is being equal to the square root of FH squared plus FV. Whoa, that's terrible. FV squared, and we come up with the square root of 281 pounds squared. Gosh. Okay. Plus, I will not be deterred. I want this pen to do what I'm asking it to do. 441 LB squared. And yet it didn't. I don't like that. Okay. Squared. Just extend that over. And when we do that math, we end up with this being equal to 523. 520. Happened again anyway. 523 pounds. Oh, that looks terrible. I really wish we were live because I can write on a board so much better than this. So I wish I could prove it to you. All right, now where's it acting? It's going to act through O in the same way that we would have done. Oh, did I not bring that in? Shoot, I just gave myself. Oh, there we go. Let me go back. Let me let you guys get the numbers first. But this should be 523. But it will act through O in the same way that we had on the example a moment ago. So I'll jump ahead to that here in just a second. Okay, hopefully you've all got that by now. And O would look like this, where O now is going to go through the center of the conduit because it's circular in this case. All right. Okay. Now I want to talk about a slightly different, but maybe more common example of curved surfaces. And this one has to do with the pressure acting on the bottom of a bottle of soda. One of the things you may have noticed if you've ever sort of played with or dealt with a 2-liter bottle of soda is that the sides of the bottle often feel kind of wimpy compared to the bottom. So there's a reason for that. What do I need to do? I need to get out of arrow mode. There we go. Okay. So let's go ahead and watch this video. So here's a Sprite bottle, 2-liter bottle. So there's supposedly 2 liters of fluid in there. We see someone open it and, there's a lot of pressure. So it comes out all over, right? Now, if we didn't do that and we just looked at the pressure that was built up, you can see that we would get to a little over 40 PSI. That's a lot of pressure. But the bottoms of these bottles somehow are able to hold not only that air pressure inside, but also hold on to whatever force the fluid is applying to the bottom as well, okay? So let's take a more simplified version. We're not going to look at one that's quite so complicated on the bottom, but we're going to just take this concave sort of a view of the bottom, and let's figure out the total forces that the bottom of the bottle is resisting to keep it all together when it's sitting on a shelf waiting to be purchased at a store and then consumed at some point. So by the way, I don't know. I think we could guess. I guess there's a vernacular around the U.S. as to whether you call it soda pop, or you use, like when we say Kleenex and you actually mean a tissue, sort of, Coke or something. So in this case, we have, we don't care what brand it is, but we have, if the bottom of a pop bottle, similar to that shown in the figure to the side here, what would be the magnitude of the resultant force acting on the hemispherical bottom? The air pressure at the top of the bottle, so inside, is a little less than what we saw in the video, 36 PSI. And the pop has approximately the same specific gravity as that of water, and assume that the volume of the pop liter remains at 2 liters. In other words, you've got 2 liters built up in there, and somehow we've measured 36 PSI to sort of figure this out. Now we're given so we're working in PSI, so remember that's pounds per square inch, and then we also have a diameter of 4.3 inches. So I guess we'll work in English units here, despite the fact that we're given a volume in liters. So let's do a quick, as a bit of a teaser. As you're going to expect, we need the volume of this fluid acting downwards. So let's convert that 2 liters of pop real quick to cubic feet, so that we at least have that for figuring out the volume, so that we can figure out the weight here in a moment. All right, so pen color, let's try green. All right, so the volume of pop, oh, I forgot how light that is. I don't like that contrast. The volume of pop is, we can't do white, that won't show up at all. Let's try magenta, see what that looks like. All right, equals, well, it looks an awful lot like red, but all right, we'll go with it. Is equal to, we said 2 liters, which, by the way, we can convert to cubic meters. 1 cubic meter is 1,000 liters. And then we need to, I just happen to have a conversion for cubic feet to cubic meters. And so we'll do that. So then we multiply by 35.31 cubic feet per meter cubed. Okay, so the liters will cancel, our cubic meters will cancel, and we should end up, when we do this math, with cubic feet, and it turns out we don't have a very big number, 0.0706 cubic feet. Okay. All right, so that's our volume. On the next slide, we'll spend some time. How many slides did I give myself? All right. Yeah, I do have one to work. Okay. So let's take a look at how this works itself out to figure out the forces on the bottom. Now, the bottom itself, of course, is all going to have vertical forces. So let's draw these forces. So here's our, I'm just going to call it our resultant force that's holding up the bottom of the bottle. But there are 2 forces acting downward here, right? One is F, I'm going to call it air pressure, air P, AIRP. So the air pressure. I don't mean F air like it's the force from the pressure of the air outside, but rather this is the internal air pressure. And then secondly, we have, the weight, right, acting downwards as well. And that's why we calculated the volume of the pop, because we're going to need to multiply that by its specific weight to get the weight force acting downwards. Okay, so of course, the sum of the forces, in this case in the z direction, are going to be equal to 0. So we have FR is acting upwards minus W minus F air pressure. Okay. All right. So we can probably calculate these forces pretty quickly. So let's do that. Let's calculate the weight. We've already got the volume. So we can calculate the weight force by saying W is equal to gamma of our pop. And remember the statement said, the problem statement said that the specific weight of the pop is equal to the specific weight of water, that's a good approximation. So we'll just use 62.4 pounds per cubic foot again. And then we multiply by the volume of pop, right, which we already calculated. So this is 62.4 pounds per foot cubed. And then we multiply by 0.0706 cubic feet. And you come up with 4.41 pounds of pop or soda, okay? So if it costs you $2, if it costs $1 a pound, you'd be paying $4.41 for a 2-liter bottle, just FYI. All right, so there's that. Now we need to figure out the force of this air pressure, right, which is also acting downwards. So that's going to be equal to the air pressure itself. I guess I don't need to put a P in there, right? P air is inside. And then we multiply that by the cross-sectional area of the circular part of the bottle, right? So this is going to be equal to 36 pounds per inch squared, PSI, multiplied by pi over 4. Now remember, we were given a diameter, so I'm just going to stick with using the diameter here. So pi over 4 times d squared. D is 4.3 inches, right? That would be the area of our circle, which is the looking down on the soda bottle. And we square that, okay? So when you work this out, F air pressure is equal to 523 pounds. All right? So real quick, before we go any further, look how much smaller that weight force is. The force that these bottles endure to keep them steady until they're bought or until they're used is mostly this air pressure. And that air pressure is there to keep the fizz from coming out of the soda, right? You have to pressurize your system. Okay, so our resultant force then that's acting on the bottom of the bottle here is equal to, we said, F air pressure inside plus the weight. So that comes out to 523 pounds plus 4.41. And ultimately, we just call this 527, and yet I have done that without looking at my significant figures. So just as an FYI, don't forget those. But the idea then is, we're somewhere in this, low 500s range for the amount of force that we have to hold in with the bottoms of these bottles. So, next time you deal with one of these soda bottles, be a little bit impressed by the engineering that goes into these containers. All right. Okay.
So we didn't really need to take into account the curved surface of the bottom of the bottle at all.
Right. In this case, you didn't have to, because it's not as if we were asking for like a pressure distribution. We just wanted the total force. Yeah, good question. This one's going to be a little different. Okay, so now we've got one of these Tainer gates that we talked about very early in today's slides. And what we want to figure out here, well, oops, I apologize. It looks like the figure got over the words. So let me read this out to you. A gate in the form of a partial cylindrical surface, called the Tainer Gate, holds back water on top of a dam, as shown at the figure to the side here. The radius of the surface is 22 feet, okay? And the length, its length is 33 feet. So 33 feet goes, into, we can call that the width or the length, but essentially it's into the plane here, right? The gate can pivot about point A, and the pivot point is 9 feet above the seat at C. Determine the magnitude and the resultant force on the gate, or of the resultant force on the gate. Okay, so all we're looking here for is FG. I want to draw a diagram for us to use, but I want to do it on the next slide so that we get all of this geometry just right. Okay, let me see. Yeah, okay. So we've said that this is 9 feet. The other thing is that this right here is 22 feet. Okay, what we're going to end up doing is just isolating this part of the gate that acts from where the water is touching the top of it down, so the submerged part. All right. So let's start on the next slide. I'm gonna redraw this figure, but just more focused on the gate interacting with the local water there. Okay. So let's see how well this works. We do something like this. We bring this down to here and over, and we said that I'm going to call this point C. I'm going to come back to a point B here. I'm going to drop down from B to go to E. This is E. And then D will be over here. And all of this is water. And this curve from C to E is our gate. All right. So the forces that we have to that we're considering here, let me change my pen color. The forces are some FG. I don't know if that's drawn in the right direction or not, but the point I want to make is that it's not perfectly horizontal, it's not perfectly vertical. And we have to deal with sort of these other forces that are coming into play here. Here's an F1 that will be the hydrostatic pressure acting on the left-hand side of this. F2 will be a hydrostatic pressure acting up from the bottom. And then we have the weight of the water in this area acting downward. Okay. So you might be wondering, wait a minute, why do we care about the weight if it's acting opposite the gate? The point will be that we still have to account within our system. So we've kind of created this little rectangular view of the world. It's fine if the weight acts in the opposite direction. We still need to take it into account when we figure out the balance of the pressure forces and the weight acting in the vertical direction to know what vertical component is acting on the gate. Okay, so it may sound extraneous, but it'll be important. Now let's go back to the center, which I believe was A. We can call that the center of this rotation, and we have this length here that we said was 22 feet, and we have B to E. So I'm going to just write this as L B to E rather than trying to draw it in there. We said that that was 9 feet. Okay. Another length. So what we're going to do to figure out the volume of water that applies to this weight is we're going to look at a volume from C, D, E, B, this whole rectangle. And remember, it's 33 feet long into the page here. And then we're going to cut out this piece right here. This sort of C to B to E piece right there. All right, so we're going to work in areas, and after we figure out the appropriate area for what's shaded here, then we're going to multiply that by the 33-foot length. All right. By the way, this is some angle that we can write in as theta. It's unknown, but of course we can find it because this length is 9 feet. This is 22. So maybe the first thing I'll do is just solve for theta. The sine of theta is equal to 9 feet. Of course, it's a ratio. It'll come out to be no units divided by 22 feet, which is equal to, well, I didn't put the intermediate here. I kind of skipped a step, but theta comes out to be 24. Oops, I should say equals. Theta equals 24.1 degrees. Okay. All right. We know we're going to need this distance L, the length from D to E. So let's just go ahead and calculate that as well. Now, one way of figuring this out is we can say that the length from D to E. Well, that's not good. There we go. D to E is equal to the length at the top there from C to B. All right? And if that's the case, then we know that this full length here is 22 feet. Right? This is just part of this radius that goes out from A. So this is going to be equal to 22 feet minus the length from A to B. All right. How do we figure out A to B? Well, luckily we have this this theta value here, right? So now that we know this angle, we could take the cosine, or we know that the cosine is this length L from A to B over 22 feet. So we can solve for LAB. So LAB, real quick, as an aside, is equal to, I probably should have done that math differently, but let's see. We said cosine is equal to LAB over, so it's going to be cosine of theta times 22 feet which comes down to the cosine of 24.1 degrees times 22 feet. Gosh, this is getting messy. I don't understand why. Okay, so when we work this out, I ended up combining this. Sorry, I didn't write the intermediate step, but LDE wow, this is awful. Okay, DE, maybe it's hearing me. Okay, I'll just speak to it. Is equal to 22 feet minus this 22 feet times the cosine, or we could write the cosine of 24.1 degrees times 22 feet. And we end up with 1.93 feet. Okay, so we've got that length now. All right, I realize we're just about out of time, so let me think. Do we want to start working through the forces? Let's do one force real quick, which is F1 acting at the left there. We'll do the other forces on Tuesday, or yeah, I'll figure out a way to communicate these to you guys. Given that I'm going to be going, I may just record the rest of this problem and then post it for you. So F1 is equal to gamma times, in this case we have water, times H sub C acting on that left side, that vertical side, times, I'm going to call this of AB, or vertical, because that's different than the horizontal area down on the bottom, which we'll discriminate here in just a moment. So this is going to be equal to 62.4. 62. Okay. All right. Let's just do all the forces a little later. My pad seems to be awfully tired or something. I can't seem to write on it. So real quick, I will finish this video and post it for you guys, and I'll let you know how I'm doing that. I think what I may do is just pause the rest of the recording and do this after my next meetings. But real quick, I wanted to ask you a quick question. When you go into Canvas and you click on the Wiley online resources, do you get a page that looks like this? Now, of course, I expect you probably won't see that, right? Because you're not instructors. But do you get this practice tab? Because if you do, one of the things that you could do is go down to the fluid statics, check this, and then the next slide for me looks like this, where I have all of these practice questions. And so my point of bringing this up is that these practice questions would be great to work on in preparing for the exam. You can see that they go along with particular sections of the book, section 2.1, section 2.2, etc. And there's a whole list of these. I just did a quick screenshot. So I wanted to make that available to you, or just let you know it's there, hopefully. But please tell me whether you can see that or not. Let me just wrap up by noting homework 5 is posted. That'll be due next Thursday before class. Alexi will hold off